Good afternoon and welcome to this Conservation Applied Research and Development webinar. I'm Mary Sue Lovenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. With me today is Mark Garofano, who is an energy engineer at the Division of Energy, where he performs engineering reviews of custom efficiency projects, and he leads the department's efforts to maintain and update the technical reference manual that utilities use to calculate savings and cost effectiveness of their conservation program. Mark is also the project manager on the research that is the subject of this webinar. Our presenter today is Joe Plummer from Franklin Energy. Joe is a program manager providing technical support and consulting services for Minnesota utilities and the Department of Commerce. Joe's work includes analysis of custom incentives, commercial and small business energy audits, deemed savings development, and he also manages CARD projects. Before we start, I'd like to go over a few webinar basics. All attendees will be in listen-only mode. As questions occur to you during the presentation, type them into the question box in the GoToWebinar panel and send them to us. We will address all questions at the end of the presentation, and if for some reason we don't get to all questions, we will answer them later and email all answers to participants. This webinar is being recorded and will be available on our website for viewing on demand at a later date. Finally, the slide deck for this webinar is available as a handout on your GoToWebinar panel, and you can download it at any time during the presentation. This webinar is one in an ongoing series designed to summarize results from research projects funded by Minnesota's Applied Research and Development Fund. The Applied Research and Development Fund was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their 1.5% energy savings goal by identifying new technologies and strategies, improving the effectiveness of utility conservation programs, and documenting CO2 reductions from conservation programs. A utility may reach its annual energy savings goal either directly through its conservation improvement program or indirectly through energy codes, appliance standards, behavior, and other market transformation programs. $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal or RFP process. Since the legislation was enacted in 2007, the CARD program has had 8 funding cycles with 22 RFPs posted, received nearly 380 proposals, and funded over 92 research projects, representing over $21 million in research dollars. As you can see by the pie chart, projects funded to date have been in all building sectors. The subject of today's webinar is the commercial industrial sector and reports on a project which investigated whether industrial high-frequency battery chargers are a viable energy savings measure that can be included in the utility conservation improvement programs in Minnesota. I'm going to turn it over to Joe now, who's going to tell us the details of the project and its results.
Well, thank you, Mary Sue, and thank you to the Minnesota Department of Commerce for providing us with this opportunity. I'm here today to give an overview of the battery charger field study, which we performed on behalf of the CARD program. It specifically looked at industrial battery chargers as used for battery-powered lift trucks. The idea for the study was hatched after a vendor presentation on high-frequency battery chargers a few years ago. The vendor talked about how high-frequency chargers can save energy compared to older, less efficient technologies, and how they have the capability to charge batteries at much faster rates. Well, we wanted to test these claims by measuring the actual performance of high-frequency chargers in the field. If our measurements confirmed the vendor's claims, it would add to the credibility of high-frequency chargers as an energy efficiency measure. My talk today will cover these main topics: background on the various types of industrial battery chargers, an overview of past research, the methodology of our field study, our findings, and finally, our conclusions and recommendations regarding inclusion of high-frequency chargers in SIP. First, some background on industrial battery chargers. Battery-powered lift trucks are very common throughout the commercial industrial sector. They're commonly used in manufacturing, warehouses, airports, and other facilities for material handling. To give you a sense of their numbers, it's our experience that the typical facility has at least one lift truck, and there are over 7,300 manufacturing facilities in Minnesota alone, according to U.S. Census data. Large facilities may have dozens of lift trucks and battery chargers. The energy consumed by lift trucks can be very high. One estimate from California puts it at approximately 15,000 kilowatt hours per year for a typical unit. Of course, the actual energy use for a given facility can vary greatly from this estimate. It's strongly influenced by factors such as how heavily the lift trucks are used in the facility and how many operating shifts per day are run throughout the facility. So, some background on the technology. The basic function of all battery chargers is to convert alternating current or AC electricity to DC or direct current electricity and deliver it to the battery. Invariably, some energy is lost in this process, which is where energy efficiency considerations come into play. All battery chargers also have control circuitry that controls the rate of charging and ensures the battery is not overcharged, which can damage it. Most industrial chargers in use today, over 75% by some estimates, are ferroresonant or silicon-controlled rectifier types. However, a new technology, high-frequency chargers, is now available and gaining market share. This type of charger is promoted as being more energy efficient than ferro or SCR chargers, and some manufacturers also claim that it is capable of higher charging rates. Many facilities today regularly charge their lift truck batteries using an approach called conventional charging. Under this approach, lift truck batteries are run down to low charge levels, ideally no lower than about 20%, then plugged into the charger overnight during off-peak hours to slowly bring the battery back to an acceptable charge level. The problem with this approach is that some facilities must have their operators change batteries, swapping depleted batteries with fresh ones to continue operating their lift trucks, while the depleted batteries are recharging. This has an operations and maintenance or O&M cost impact and hurts productivity. There are also health and safety risks associated with battery changing. In contrast, high-frequency chargers, as we learned from this study, some ferro and SCR chargers as well, are sometimes advertised as offering fast charging or opportunity charging capability. Opportunity charging means plugging in during breaks in the workday and rapidly recharging the batteries to sufficient levels. Opportunity charging avoids the need for battery changeouts and associated cost and productivity impacts. The Electric Power Research Institute, or EPRI, performed large demonstration projects in the early 2000s, demonstrating various workplace non-energy benefits from fast charging. While these benefits exist, customers and utilities should be aware that there is the potential for higher demand charges with opportunity charging due to higher charging rates, as well as shifting charging events to peak periods. Higher demand charges could erode some of the energy savings from upgrading to high-frequency chargers. There are 4 types of industrial battery chargers that are commercially available: ferroresonant, silicon-controlled rectifier, hybrid, and SCR chargers. Ferroresonant and silicon-controlled rectifiers are thought to account for about 80% of existing stock. The numbers shown here are actually from California. They're from a PG&E study from 2009. But the local distributors we spoke to in Minnesota indicated that they are roughly correct for our state as well. The power conversion efficiency and cost ranges here are also from that PG&E study. As you can see, high-frequency chargers were shown to be, on average, about 7 percentage points more efficient than ferro or SCR. However, their median cost is also higher. Battery charger energy efficiency is commonly expressed in terms of 5 different metrics. The first, charge return factor, compares the amp hours returned during a charge cycle to the amp hours delivered by the battery during discharge. This factor ideally ranges between 1.05 and 1.15. Power conversion efficiency is the ratio of DC output power to AC input power. Maintenance power is the average power consumed by the charger when the battery is connected but not actively charging. No battery power is similar, except it's the average power consumed by the charger with no battery connected. Finally, power factor is an energy efficiency metric, and it basically expresses how well aligned the voltage and current waveforms are in AC electricity. Ideally, the power factor should be 1. The first 2 metrics, charge return factor and power conversion efficiency, are usually the strongest predictors of charger energy use. High-frequency chargers are thought to have a technological advantage in terms of power conversion efficiency and power factor. The remaining metrics, such as maintenance power and no battery power, as well as charge return factor, are a function of how well the battery charger control circuitry is designed. They're not closely correlated to the, or they're not a function of the battery charger technology itself. So the energy efficiency of high-frequency chargers was studied in a systematic way by PG&E in the late 2000s. Formalized test results were released in 2009 that demonstrated a higher average efficiency for high-frequency chargers relative to older technologies. Our goal of this study was to investigate the performance of high-frequency chargers in actual facilities from both an energy perspective as well as a non-energy perspective. Aside from measuring energy savings, we also wanted to assess any productivity or O&M benefits to the facilities as a result of the capability to opportunity charge with high-frequency chargers. Before getting into the field testing, I wanted to touch briefly on past research on industrial high-frequency chargers. I've mentioned the PG&E studies a couple of times now. These studies really laid the groundwork for high-frequency chargers as an energy efficiency measure. These studies grew out of the development of a battery charger test procedure, initially for consumer battery chargers, by the California Energy Commission in the early 2000s. The utility companies PG&E and SCE adapted this procedure for industrial battery chargers, and it was eventually adopted into state law in December of 2008. PG&E's Emerging Technologies program sponsored formalized testing of industrial battery chargers, and the results were published in 2009. This table summarizes the PG&E test results across the 5 different energy efficiency metrics I discussed previously. Here I have orange fill indicating where the average charge return factor fell within the ideal range of 1.05 to 1.15. Excuse me. Yellow fill indicates the best performance in each metric, which could mean highest or lowest depending on the metric. As you can see, high-frequency chargers were best in class in 3 out of 4 parameters and had an ideal charge return factor within the ideal range. On average, their power conversion efficiency was about 7 points higher than Ferro or SCR chargers. It is important to realize, however, that there are ranges for each metric that usually overlap. For instance, in terms of power factor, Ferro and high-frequency units have ranges that closely align, even though the highest power factors were seen with high-frequency chargers. This observation has important implications for how high-frequency chargers are treated in DSM programs. EPRI completed 3 large demonstration projects, which I mentioned before, of fast charging and automobile assembly plants in the early 2000s. Some of the high-level results they saw were, 1, increased productivity and reduced labor costs from not having to change batteries between shifts or at the end of the day. 2, improved safety through reduced risk of injury associated with battery changeouts, as well as reduced risk of vehicle collisions in battery changing areas. 3, parts and maintenance savings generated by not having to purchase extra batteries and having better part protection. Battery and part protection increased as batteries were less likely to go below 20% of charge capacity, which can damage batteries as well as connections. And now I'm going to switch gears and talk about our study, beginning with the methodology. The focus of our study was field testing. We performed evaluations of high-frequency battery chargers in 9 facilities across Minnesota and South Dakota, comprising a total of 13 charging stations. The field testing began with pre-monitoring, in which energy loggers were installed to monitor each facility's existing Faro or SCR chargers for a minimum of 2 weeks. For the post-monitoring phase, we installed high-frequency chargers on a temporary basis, and similarly installed energy loggers to monitor the high-frequency energy use for a minimum of 2 weeks. The measurement equipment consisted of a Fluke 1730 energy logger or equivalent, which logs the AC input power at 1 minute or 5 minute intervals, depending on the specific logger type used. For one site, we also used a Douglas DataTrack battery monitoring device in order to simultaneously measure DC output power. The photos to the right show one of the charging stations in the study. The top picture shows 2 existing SCR chargers, one of which was monitored during the pre-phase. The lower picture shows installation of the high-frequency charger at the station, which replaced one of the SCR chargers. We also performed interviews of facility managers at sites 8 and 9 to understand any productivity benefits they saw with the high-frequency chargers. Now I'm going to describe some of our findings. First of all, I want to say that the study had many challenges. The big one was finding good test sites. Originally, we looked to the 3 main industrial battery charger distributors in Minnesota to help in this area, but several months went by with little traction from this sector. Thereafter, we primarily relied on our subcontractor and utility friends for leads. Many leads that came to us had to be rejected because they did not meet our screening criteria in terms of operating shifts or lift truck usage. The sites that we did accept, for the most part, had no need for opportunity charging, which made it difficult to evaluate non-energy benefits. Finally, at 2 sites, we were not able to get a complete set of pre and post data. Only one or the other was able to be collected. On top of the site limitations, there were also limitations with our intended testing methodology that became apparent as the study progressed. For one, we generally just had 1 or 2 loaner high-frequency chargers available to us. This meant that some existing chargers could still be used by operators during the post period, which had the effect of confounding the energy comparisons. The site photos I showed previously are a good illustration of this problem, where only one of the 2 existing chargers was replaced by a high-frequency unit. Second, although we intended to measure power conversion efficiency at every site, we struggled to find a solution for doing this without interfering with operators' use of the chargers or installing instrumentation that could void the charger warranty. Aside from not being able to measure conversion efficiency, this meant that we could not control for differences in lift truck usage between the pre and post periods. Finally, we learned near the end of the field testing that opportunity charging may not have been enabled by the distributor on all high-frequency units that were tested, which meant that the peak demand effects may have been artificially limited by this setting. Overall, as I'll show on the following slides, our testing yielded some puzzling, inconsistent results. The following table summarizes the results at each site and charging station. The lower section of each table shows the change in key parameters across the pre and post periods, with the pre period comprising the existing chargers and a pulse period comprising the high-frequency charger. I've shaded cells with a significant increase in green and cells with a significant decrease in red. Because the pre and post monitoring durations were usually different, I normalized the energy usage by charging event as well as day. Based on the PG&E results, one would expect there to be a consistent decrease in kilowatt hours consumed per charge and a consistent decrease in the kilowatt hours per day. However, a quick glance at this table shows this was not the case. In fact, there was a major increase in kilowatt hour usage at Site 2, Station 1. Peak demand increased at all 5 stations shown here. However, there is no consistent correlation to the average length of charge. One would expect there to be an inverse relationship between these parameters, but this was not the case in every site. Here are results for the remaining sites where we have a complete set of pre and post data. Here, most sites showed a decrease in peak demand. Most sites also showed a drop in kilowatt hours per charge and per day. Those sites 3 and 4 are exceptions. I also note that the power factor dropped significantly at Site 4 and 8. This was not at all expected based on the PG&E results. Overall, these results are puzzling. Kilowatt hours per charge did not consistently decrease with the high frequency units as expected, nor did kilowatt hours per day. Also, the high frequency chargers did not consistently have a higher power factor. Some of the existing Faro chargers, namely at sites 1, 3, 4, and 6, had a very high power factor of 0.9 or greater. These results are not surprising in themselves, as the PG&E results showed overlapping ranges in this parameter for Faro and high-frequency units, as I described previously. What was surprising was the very low power factors measured with the high-frequency units at sites 4 and 8, only 0.75 and 0.62, respectively. Finally, the high-frequency chargers did not consistently produce higher peak demand, as would be expected if their charging rate was higher. As I mentioned previously, we were able to measure power conversion efficiency at only one site with the aid of a battery monitoring device. Unfortunately, this device did not have the capability to log discrete data measurements. Instead, it produced an event summary which could be exported with cumulative amp hour measurements. Using event summaries timestamps, I was able to do a rough comparison to the AC input data from the energy logger. The results of this exercise are shown in this table. While these results do point to a higher conversion efficiency for the high frequency unit, the actual numbers here are a little bit suspect. You can see that with the SCR charger, a conversion efficiency of only 51% was measured. Then when it was switched to the high frequency unit, an efficiency over 100% was measured, which is impossible. Customer interviews were completed at Site 8 and Site 9. As the table indicates, Site 8 was a mid-sized commercial printing facility with only 2 SCR chargers and 2 lift trucks. Site 9 was a large medical device manufacturer with 35 Faro chargers and 30 lift trucks. Neither site switched to opportunity charging during the testing, so the facility managers could not speak to any productivity gains with the high-frequency chargers. The operators were indifferent to the high-frequency units because, just like their existing chargers, they would simply plug in and walk away. In terms of important factors when considering a new battery charger purchase, some insight was gleaned. Both sites indicated that reliability was their #1 concern. Site 8 had no need for a faster charging rate given their relatively light lift truck usage. Site 9 had very heavy lift truck usage and was interested in this feature. for productivity as well as battery health, i.e. not going below 20% of charge. Both sites were interested in energy savings in terms of the financial benefits. Now I'd like to offer some concluding remarks and recommendations. From our results alone, it is difficult to assess the energy and peak demands of high-frequency chargers due to the site and testing limitations in the study. Power factor is one area where our results are more reliable, however. In our limited sample, no clear advantage was seen for the high-frequency units. The very low power factor is seen at 2 of the sites with the high-frequency units are cause for concern and suggest that potential buyers should verify this parameter before committing to a purchase. The results for sites 8 and 9 demonstrate that the value proposition for high-frequency chargers varies greatly. Sites with light lift truck usage would likely see long paybacks from upgrading to high-frequency chargers and would probably have little need for opportunity charging. At the other end of the spectrum, sites like Site 9 with heavy lift truck usage could see a very good return from investing in high-frequency chargers, both from an energy savings perspective as well as an opportunity charging perspective. However, as I mentioned previously, the premise that high-frequency chargers alone enable opportunity charging may be flawed. During the course of this research, we found examples of new Faro and SCR chargers that are promoted as having fast charging or opportunity charging capability. No matter what technology is selected, customers that are interested in opportunity charging should be aware of possible impacts on their peak demand that could offset energy savings, depending on their rate structure. Going forward, we would offer the following recommendations based on this study. First, the limitations of the field testing make it difficult to draw conclusions on the actual performance of high-frequency chargers compared to older technologies. Many utilities currently incentivize high-frequency chargers through their custom rebate programs. This is an appropriate practice going forward. Custom incentives for high-frequency chargers should be based on a careful analysis of the existing chargers compared to the proposed charger performance, taking into account the operational patterns of the facility, such as average charges per day. Second, if prescriptive incentives are desired, qualification standards for the proposed equipment should be based on energy efficiency metrics, such as power conversion efficiency and charge return factor, rather than technology alone. Ideally, all energy efficiency parameters should be rated according to the test procedures defined by the California Energy Commission. And with that, I'll conclude this presentation and take any questions you may have.
Thanks, Joe, for that great presentation. If you have not already done so, type your questions into the question box in the GoToWebinar panel and send them to us. Now I'm going to turn it over to Mark, who has been monitoring your questions as they come in. Mark, do you have any questions for Joe?
So far, I have a few questions for you, Joe. The first one we have is that you said that in your conclusions that potential buyers should verify power factor before purchasing high-frequency chargers. How would you suggest the buyer do that?
Yeah, thanks for that, Mark. I would say the ideal way would be to ask the distributor for a loaner unit to actually test and then actually use it and measure the power factor with a power monitoring device. That's the best way to measure that actual factor, as well as any other factors associated with the energy use.
Okay, thanks for that. The next question we have is there anything more you can say about why you think there were those discrepancies between what you expected to find in the study and what you actually found? In addition, are there implications for verifying savings from high-frequency battery chargers and utility programs?
Yeah, I guess, well, first I would say, as I discussed in the presentation, our testing was not tightly controlled. This was by design because we wanted to test the performance of these units in the field. However, there are limitations with this approach. One is that there could have been differences in vehicle usage during the pre and post periods that would impact total energy consumption. So, for instance, if the lift trucks were used more heavily in the post period, then they would naturally consume more energy from the battery chargers. Also, we could not control for the state of battery charge at the beginning of each charge, which could possibly explain some of the differences in kilowatt hours consumed per charge. As far as implication for verifying savings, ideally, any potential rebate projects should take into account the actual performance of the existing and proposed chargers. You can do this through an engineering analysis using the energy efficiency metrics measured according to the California testing standards, as I mentioned. Or you could go one step further and actually meter the equipment. Basically, either approach is justified by the fact that even looking at the PG&E results, there was a range of values measured for every energy efficiency metric. For instance, if you look at the least efficient high-frequency charger, it's barely more efficient than the most efficient ferrule charger. So the savings between those two units would be very small. All in all, I would say that a high-frequency charger should not be rebated solely based on the fact that it's a high-frequency unit. It should be analyzed according to its actual performance, not its assumed performance.
Okay, thanks for that explanation, Joe. And then next question we have is, what did you find out for current prescriptive measures for high-frequency chargers in your research?
Yeah, I would say overall we learned that prescriptive incentives are not very common for high-frequency units. Even the California utilities that pioneered high-frequency chargers as an efficiency measure do not seem to offer prescriptive incentives. There are some examples out there. Locally, Missouri River Energy Services is one utility that offers prescriptive incentives. They cover Minnesota as well as Iowa and the Dakotas. They offer $100 per high-frequency charger based on 1 or 2 shifts of operation, or up to $300 per high-frequency charger for a 24-hour operation. Those incentive levels are pretty typical compared to the other examples that we found. Generally, they vary between $100 to $300 per charger or per shift, depending on the utility. But overall, like I say, the vast majority of utilities seem to rebate these through custom rebates.
Okay, that is all the questions we have on our list at this point. So.
Okay. Thanks, Mark. Thanks, Joe. So I'd like to just do a couple of wrap-up information. First of all, as I mentioned before, the recording of this webinar, as well as the final report, should be available in a few weeks. We'll send out an email to webinar participants to let you know that they are available. When available, you can link to them from either our webinar quick link or the Card Search quick link located on the Applied Research and Development, or R&D, webpage as shown here. The R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out. The web address is at the bottom of this slide. Well, thanks for participating in today's webinar. We appreciate your interest in the results of CARD projects. Before we leave, I want to take this opportunity to mention 3 upcoming CARD webinars. The first one on October 5th, which is just next week, next Thursday, the Center for Energy and Environment will present the results of their assessment of cold climate air source heat pumps in single-family homes. On December 7th, Michaels Energy will discuss their project, which tested 2 ongoing commissioning approaches to improve the energy efficiency of outpatient medical clinics in Minnesota. And on December 14th, the Center for Energy and Environment will again conduct a webinar on their field study to determine the increased efficiency resulting from the installation of an innovative moisture and heat transfer retrofit device on residential furnaces. Announcements about upcoming webinars and other news related to the Minnesota Utility Conservation Improvement Program can be found in the SIP newsletter. To sign up for the newsletter or to receive email news on a range of other energy topics, use the link on this slide to go to the email sign-up page on the department's website. In the meantime, please contact me if you want more information on how to sign up for these upcoming webinars, or if you have questions or feedback on the CARD program. Also, let me know of any suggestions for improving these CARD webinars to make them more relevant to you. Thanks again, and have a good afternoon. Joe, are you still there? Probably not.